the Astrophysics Institute of Andalusia for inviting us as representative of the Spanish science industry to be here to share with us some thoughts and some ideas. First of all, my presentation is going to be a general one. After me, some companies, some industrial companies are going to present some specific projects and their capabilities. But usually I try to say something about science industry. And let me say something that for you is quite evident, but I think it's useful to remind that. If we were a Martian looking to the Earth, probably we will notice that humanity is in a special point of evolution. For first time in 100,000 years, the human species can control its own evolution because of the Human Genome Project. That is one important thing for the future, and it's happening now. And the second thing is that this is our home, and what a beautiful home, blue, green, white, and so on. But for first time in 100,000 years, we are experiencing Earth spillover challenges. Until now, everything was without limits. We have enough ground, enough water, enough air, and so on. But now, we have demographic challenges, food challenges, health, energy, contamination, resources depletion, etc. And all these problems, because they are real problems, are going to be solved through three ways: science, technology, and ethics. Because we need ethics in order to use in the right way the technologies that the science made possible. Basic science is developed at bigger scientific research facilities like particle accelerators, synchrotrons, power lasers, optical telescopes, neutron sources, radio telescopes, biology laboratories, and so on. Science industry is the industrial activity sector, which includes the companies that devote some part of their activities to the design, engineering, manufacturing, and maintenance of those large scientific research facilities and their singular instruments. What are the main fields of science industry? Obviously, because we are industry, we are looking to the place, to the science sectors where most of the money, most of the market is there, because industry has a main objective that is to produce in some way new jobs, new sources of money in order to pay taxes and so on. The six different sectors where we are looking is particle physics, so accelerators, neutron sources, synchrotrons, etc. Fusion should be energy, but because the singularity of this project and the quantity of resources that are involved, we have taken out this sector, science sector, as a singular one, so it's fusion. Astrophysics and space science, biology and life sciences, energy and ICTs, that means energy only the scientific part of new energy sources. For instance, aeolic for us is just another industry, is not inside science industry. And an important point that is large scientific research facilities, because you will know that about 30% of the budget of a new large research facility is devoted to not to the main machine, not to the accelerator, not to the telescope, but to the building and to the special services that are needed for this facility to work properly. So if 30% of all the resources are devoted to that kind of job, for us as an industry is important. What are the main technologies? We will say that most of the advanced technologies are inside the science industry sector. But some of them are, for instance, superconductivity of magnetism, especially in particle physics, in accelerators. Cryogenics, that is a transversal technology that is also needed in astronomy. Vacuum and ultra-high vacuum, also transversal. Robotics and control systems, of course. Radio frequency systems, power radio frequency also. Instrumentation, sensors, detectors, high precision mechatronics. Some of the companies with a high level of capability in high precision manufacturing have been previously in the science industry sector. Remote handling, of course, because some moments we are working with extreme conditions, for instance, radiation or outside in space, so we need to master remote handling. New materials, of course. If we are talking about fusion, we need to have materials that are able to endure something like 100 million degrees centigrade and some levels of radiation. So we need to research in this kind of new materials. And of course, also special power sources. Because we are talking about industry, let's give you some ideas about this market. And it's important for you also as scientists to know that there is a market, a very important market behind your work. In Spain, we have calculated a market, a year-to-year market of about 491 million euros per year. In Europe, it's something less than 10,000 million euros a year, and on the world is at least 40,000 million. I say at least because in some countries, science industry is very much related with defense or home security, and so those kind of budgets are difficult to know. But anyway, this figure is just checked with some other organizations. So we can say that at least 40,000 million euros are devoted to large research facilities on the world. Just to give you a number, we used to say that on the world there is about 15,000 accelerators. Most of them are used for medicine or hospital care. But about something more than 100 are big accelerators devoted to research. And some more new accelerators are in the moment of building, so this is growing. Big research telescope, we have a list of about 326, and fusion facilities, about 40 on the world. It's not only the big project, ITER, as you well know, but also the tokamaks and the related instruments and installations that are all over the world. Most of them working for ITER or for some other fusion technology, alternative fusion technology, like in the United States. Going to the Spanish scenario, in Spain we have something like a roadmap of singular scientific research facilities that it's called ICTS roadmap. This is the map, and you can see the different facilities. I would say most of them are medium-sized facilities in the size of 180 million as a maximum. For instance, the Gran Canaria telescope, the Gran Tecan, is about 180, and the synchrotron near Barcelona is about 200 million, etc. So the maximum budget is like this, so it's not a large facilities map. Anyway, in red you can see there the Andalusian ICTS, so it's related with Calar Alto, and in yellow you can see some other astronomical facilities that are also included as ICTS. Going to astronomics, making a zoom to our field of talking today, those are the main astronomical observatories in Spain. Roque de los Muchachos in the Canary Islands, It's a very nice one. Recently, they got the Cherenkov telescope array ubication, so there is already 2 instruments called MAGIC, and now they are installing the rest of the telescopes. Observatorio de Sierra Nevada, here at about 40 kilometers from this place. Observatorio del Teide, also in the Canary Islands. Calar Alto, of course, you know, and is the theme of today. Lleves Astronomic Center in Guadalajara, in the center of Spain. The European Space Astronomic Center in Madrid, that is a reconverted center for tracking satellites. IRAM, here also near OSN. Javalambre Astrophysics Observatory in the northeast of Spain. Madrid Deep Space Communication Complex. So those are more or less the main one, but later we have a list of some other professional observatories in the rest of Spain. You see in the map the red points are the important ones, and in blue, in deep blue, the less important ones. So there are, as you well know, probably Spain is between 3rd, 4th country in astronomic production, scientific astronomic production on the world. Science industry market for us is composed or divided in 3 different areas. One of them is the national ICTS map that I have just talked about. The second one is the international Spanish contribution to some other big programs or projects like ESO or ESA. Because Spain pays a part and contributes to those organizations, has also the right to contribute in kind or to go for building new instruments. But there is also the third area, that is what we call the free market, the science free market. So some universities, especially in United States or in some other areas, have the autonomy to buy, to design and to buy where they think is better. So our companies are working also in this free market area. Well, the Spanish science industry is composed by about 300 first-tier companies, so companies that work directly with the large facilities, and another 400 more or less that are subcontractors. Sometimes these subcontractors even don't know that they are working for large facilities, are just subcontractors. And furthermore, there is about 120 universities, technology centers and singular laboratories that are involved in this industry of science activities. Our association represents a part of these companies and is the only representative recognized by the Spanish ministries, but to represent only a part of those companies. Anyway, our association has contributed to create another organization that is called the Technological Platform of Science Industry in Spain, Induciencia. And in this space, we work not only with our associated companies, but with other companies that are not members of the association, and with the centers of research and the large scientific facilities. That way, we try to cover the whole scenario of the industry of science. Just to give some examples, we have here some companies, I'm not going in detail, of what they are doing in different fields of science industry. So you can see electromagnetism, radio frequency, special instruments for space, and so on. For us, science industry, that is a message we try to convey continuously to our political officials, that science industry, first science and later science industry as an associated organization, has a relevant impact on society, not only in science. And those impacts are, of course, economic market value. We are talking about an industry. Perhaps it's not so important as car industry or appliances, domestic appliances, or even aeronautics, but has quite a size, and also has some collateral markets, because it's normal that a company that is involved in science industry is at the same time involved in aeronautics or in medical devices or whatever. It's very difficult to find a company that is 100% related or with activity in science industry. So the impact of the technology that is derived from science industry is impacting in some other collateral markets. The technology value, because science industry is intensive in research and development, in new processes application, special ways of welding and so on, is also a field where most of the times the final product needs to operate in extreme conditions, like radiation, without gravity, and so on. Early assimilation of brand new technologies. Another impact is education, basic science development, and social value. Of course, this is it's evident. Reference value, the companies that work, for instance, for CERN or for the Astrophysics Institute here, has already a value as an example. I am able to work for this very exigent organization, so I am capable to do other things. So the reference value is important. And also the new scientific facilities location. The impact of a new large scientific facility is very important in a certain regional area. I remember now the studies made by CERN in Switzerland with the same methodology and with 20 years in difference, the same study, and both times the result were that for each Swiss franc that was invested there in the CERN, 3 Swiss francs were impacting in the industry and in the social environment that was around. Another study in Fermilab in the United States gave a figure of about 7-1 instead of 3-1. The difference, the main difference, is that in this second study, they had in mind the indirect impacts, even the value, the money that was considering as a doctorate, how much money gives to society after each doctorate. So perhaps it's a little bit high, but 3-1 is just a conservative figure. Well, as I told you, INEUSTAR is the Spanish Association of Science Industry. It's a private, professional, and non-profit organization. The membership is national-wide and has not only national activities, but also international activities. We have agreements in Japan, in Korea, we have European projects, etc. And includes industrial companies that have relevant activity on the industry of science. INEUSTAR is the European Pioneer Association and is the second association on the world. The first industrial association for science industry is the Australian one, Science Industry Australia. And we are trying, one of the main objectives of our association is to try to structure the European science industry scenario. And as I told you before, we are the technical secretariat of the Spanish Science Industry Technology Platform Indociencia, which logo you have there on the right. One of the things we do is this structure of capabilities. So I have left some diptychs for you to consider. We have a diptych for each one of the different sectors in the science industry. And this one, this blue one that you have in your hands, is the one devoted to astrophysics and science and space sciences. Not all the companies are there, just the companies that give us their information, and we have the possibility to contrast and to check that this information is right. So you have the most frequent technologies and the companies. And on the back side, you have the name of the company with a website, so it's very easy to use if you need it. Well, also, another thing that we do is to promote the Spanish astrophysics capability in different places, like, for instance, SPIE, as you know, is the most important international conference on telescopes on the world. And these pictures are the pictures from this year that was held at Edinburgh, and we had there, I would say, the biggest national stand of all the present ones. Well, Cármenes, just going to Calar Alto. Cármenes is an example of collaboration. You know what is Cármenes, so we are not going to go in there. But around 10 different Spanish science industry companies were involved in Cármenes. Those are the companies, as far as my list is true. These are the Spanish companies and the tasks they develop. For us, Calar Alto is one of the main present and future European astronomy sites. We like to think that is one of the important or the most important observatories in continental Europe, because we have also the Canary Islands that has a bigger number of observatories and telescopes, but this is outside continental Europe. Calar Alto has the full support from the Spanish science industry. Probably you know that some years ago there was a problem when the budget problems began in Spain, and at that moment the association was not the only one, but one of the organizations that supported Calar Alto in front of our government and the institutions that needed to have the decision to support and to follow with Calar Alto activities. That support will be enhanced in the future because there is an agreement that is just in the making between our association and the CSIC through IAAs, through the Astrophysics Institute of Andalusia. And this way will increment the collaboration between the industries and the activities in Calar Alto. We think that Calar Alto, through Cármenes and other instruments, will make an extraordinary contribution to a better knowledge of the next human frontier. At the beginning, I talked about the human challenges we are facing now. The real thing is that our next home, we expect beautiful homes, are out there. So the work we are doing here in space science and in astronomy are vital in order to have this future make true. Astrophysics and the related industry will be at the forefront of the new border of humanity, space. We are going to be in some other places. And Calar Alto, of course, is there to play a relevant role. The Spanish science industry, the part, as far as I represent a part of it, is ready and willing to contribute, collaborating in the building of the instruments that are needed and the facilities that are going to come. Thanks a lot, and if you have some questions.
Information. I mean, for example, imagine that a scientist wants to build an instrument and addresses to you. That will share the information in the companies, or how will you work?
Well, that's a very interesting question and not an easy one to answer, because we want to do many things, but the resources sometimes are not there in order to do that kind of things. Anyway, in our statutes, the main thing is to promote science industry. That means to promote our associated members in all the ways we can, and I'll go in there, but also other agents in science industry that are not members of our association, but represent capabilities. Some of them can be members later when they want. Some of them are just other kind of organizations, like a center of research, that cannot be a member of the association, because in the association the members are always only industries. Okay? That is why we have created another space, another working space, that is the technology platform. There, because this is supported by the government, and so is supported by the taxes of all the Spanish people, there all of the agents can be working with together. Okay, going to the activities. The first activity is to structure the sector. This is very important. It's a long-term activity. For instance, there was no a catalog of the capabilities of the Spanish science industry. Even the name doesn't exist. In some parts of Europe, when you talk about science industry, they don't understand exactly what you mean. So there is a work to do there. Now we are working with the Danish DTU, we are working with the Belgian Agoria Association, we are working with some other associations and organizations in order to structure at the same time not only the Spanish science industry, but also the European one. This is going to be a long-term task for our association. That's one part. Another part is to promote the capabilities, trying to understand where we are strong, where we are weak, and what measures we can put together with the authorities in order to cover these holes, if it's interesting or not. So it depends. Third one is to increase the returns, the economic returns of the Spanish contribution to international facilities. So if we contribute with, let's say, 400, 500 million a year, and for instance, we see that for CERN, the Spanish fee is about 70 million a year. This is the fourth or the fifth contributor. So it's necessary to have returns from there, either in instruments that the CERN is buying outside, or in time for our scientists, or in research and development activities, or whatever. So we need to increase these economic returns in order to have an impact for the money, for the resources we are putting in the large research facilities. To promote our capabilities in external events. For instance, in the last 3 years, we have been present in IPAC, that is the biggest international conference for particle physics. In SPIE, is the second time. The first was in Montreal, and the second was in Edinburgh. We have been in OPIE in Yokohama, that is for photonics, also for astrophysics, and so on. SOFT for fusion, ISFNT also for fusion, etc., etc. And there we tried to put together a common place for all the Spanish companies, supported by the Spanish authorities, with some grants, with some common decoration, to make value chains more understandable, etc. So these kind of tasks that are very common to the professional associations is the kind of job we try to do in our sector, in science industry sector.
Thanks a lot. Thanks, Francisco, Javier. Maybe one last quick question.
Yeah.
Hello, Javier. Thank you for your talk. It was really nice. Just to basically congratulate you for the fact that, in part, thanks to Star and also the effort of the different companies that are behind the Industria de la Ciencia, just to highlight also to my colleagues how present the Spanish industry is in the astrophysics business or in the astrophysical instrumentation worldwide. So I think we should recall LSST,
right.
Astrofeito,
right, of course.
With the Davis American Solar Telescope. So for me, it's something to be proud of, to see how many Spanish industries are actually, all over the world actually, putting the name of those companies in first major facilities. Just to comment, it was really nice to see, I think it was at the yes, one of the spies, to see the person from LSST announcing that Astrofeito, he couldn't even pronounce properly the name, that Astrofeito had won the contract for the
Mhm.
So I think it's something that I encourage you, of course, to keep doing, and it's really nice to see.
Thank you. Thank you.
Thanks again, our speaker.
Okay, thank you.
So the next speaker is Ismael Martinez Delgado from the Fractal company, well known by astronomers.
¿Cuál de estos vídeos?
El verde, el verde.
Pues vamos a ponerla.
Es que no sé si al
Sal de
final
aquí,
la
sal de aquí.
salida o algo, sí.
¿Cuál era la tuya? Tengo memoria de pez.
A ver, esta de...
Sal de aquí, cierra esto, Jorge, por fin.
No, pero no hace falta.
¿No? Es para no...
Ah, pero la tienes en PPT.
Sí, pero se veía muy bien y no lo hemos podido copiar. Entonces simplemente, pues te he dicho que cerrara esto para que no hubiera cosas abiertas.
Que pensaba que las habías pasado.
No lo hemos podido pasar porque eran todas PPTX y hemos visto que desde el... ¡Ay!
Pues antes se ha visto muy bien. Si queréis pongo el portátil, no sé.
No, pero si se veía bien con el... ¿Por qué te ha salido de la VBox?
Pero está en Windows ya. La vi.
Sí, no, que, o sea, con el pendrive la hemos abierto en el VBox estupendamente, sí. Solamente te decía que cerrara esta...
Antes han hecho una prueba, pero si
Sí,
queréis que saque el portátil.
pero, exacto, ahora, perfecto. Ahora abre el pincho, sí.
Está abierto.
¿Dónde?
Está aquí.
Ábrelo y ya está, y sale muy bien. Hemos hecho una prueba muy buena.
No. Ah, pero
Ah, que entonces es que no se abría en el VBox, se abría... Ah, vale.
no sabía en el Windows. Espera.
Es verdad.
Ponemos el Windows. ¿Cuál es este? ¿No? Será este. Sí.
¿Sabes? Simplemente pinchando en el pendrive se veía muy bien. Esto no está saliendo en YouTube. Alberto, ya sé quién eres. Se veía muy bien.
No, yo soy Ismael.
¿Ah, sí?
Alberto es mi hijo.
Es verdad, he visto una foto. Ay, de fractal, te veo.
Ahí tienes.
Muchas gracias. Venga.
Está yendo.
Seguro que no queréis que ponga... El caso es que antes lo han puesto bien, el portátil.
Hello, good morning. I'm going to talk about Fractal, a Spanish technological company dedicated and focused on astronomical instrumentation that take advantage on the formation experience and of our team that we have been formed in different research centers, public universities, and we have been working in the GTC project. We are a mix of astronomers and different engineers working in different topics all related with astrophysics, like management, system engineering, optics, optomechanics, detectors, and software. Well, we got our skill in the GTC project. Some of us working for ERMER, a low medium resolution spectrograph for GTC, for all the whole project. So we took experience in the assembling and characterization of detectors, and in the optical design, optomechanical design, assembly, alignment of an instrument, and of course we work, some of us, we have been working in the mid-infrared spectrograph MIDI, a new instrument for the new space telescope, during the flight model, in the characterization, test, and the verification process before its delivery to NASA. What does Fractal offers to our customers? We give services, always focus again in astronomy, in management, system engineering, in instrumentation. We have several branches, which are optics, optomechanics, detectors, and cryogenics. In software development and BPH distribution, and of course in training. At the level of the management, we produce the work package definition and distribution. We produce the schedule and the time scale of a project at different levels, the whole project or some parts of the project, the cost of the project. And here you can see some of the projects where Fractal have been involved or is still involved, like in Megara, like in San Pedro Marti in the old project, the Twin Telescope. But now Fractal is directly involved in the new project of San Pedro Marti, the new 6.5 meters telescope. Now actually Marisa is in the PDR of the building of the new telescope in Mexico. So that's the reason why I are giving you her talk. And of course, you know, or most of you, you know, in Carmenes, the level of the system engineering, well, we produce the system engineering plans, the RAM plans, the safety program plans, and well, most of you have worked directly with Anna, which is our system engineering. And of course, again, we are involved in several projects, and now in Megara and in San Pedro Marti. We have been working in the past in Carmenes on our projects. Well, in the instrumentation, we have experience in the design, defining or giving help in the designing of the scientific requirements and assembly, optical, optomechanical design. And in optical design, Fractal has been involved in several projects, but some at different levels for the whole project, like for example in Megara actually, and in the past for ACAM. But at the level of refurbishment of a new an instrument that has been built in the past, and it needs some modifications in some parts of the instrument, not at the whole instrument, like Albireo and spectrograph for the observatory of Granada. In the optomechanics, Fractal is actively working now in Megara again, which has produced all the mechanical design, and in other projects like the coronagraph for the Salamanca University, and for a project of a telescope of 6 meters for Calar Alto and other instruments. Well, I would like to talk in this point about WASAT Photonics, which is an American company, and we are a partner with we are partner of this company, and we are exclusive distributor of their products. WASAT Photonics is specialized in the manufacturing of BPH gratings, and in all of the projects that Fractal has been involved, has distributed or have implementing this their volume phase, like in Elmer, RS, or even the Megara. You can see on the left and in the center for the new Raman spectrograph that is going on board the ExoMars rover. I would like to talk about our collaborative with the University of Complutense, because this is a very nice and a very good example of collaboration between the private companies and the public research centers or public centers. And this collaboration gives us the opportunity of make our integrations or test and analysis of all the instruments that we are working on or performing. In these facilities, there is what we call a test bench for CCD characterization, where we obtain the efficiency curves, the gain, and we made the assembly and all the characterization of the detector in cleaner rooms, against with the Complutense University. And at this point, we have to say that we give to our customer support and consultancy about detectors always specialized for astronomical applications at different levels. As you can see here in this picture, for example, several detectors that Fractal has directly characterized and assembled, like Carmenes, well, the visible detector of Carmenes, and those of Megara. And in this facility with Complutense University, we make the characterization of all the BPH that we design, because basically I would like to say that we specifically design the BPH attending the requirements of our customer, and then we send the design to Wasatch Photonics that make the hologram. And before it delivers the BPH to our customer, we perform several tests on these facilities, like study of transmission, the line density. So we check all this thing to see if the BPH that we have designed is on the requirements. Test of surface quality or assembly. You can see in the top of picture of these frames, you can see our colleague Ernesto gluing a medium resolution BPH of Megara, which is sandwiches between two prisms. In this picture is in that process. Another topic that Fractal is working actively now is in the treatment of optical fibers, where we have built what we call the gluing station for gluing all the micro lensings to the mini bundles of the MOS of Megara, characterizing the transmission, the FRD effects, and of course in the LCD for Megara and in other projects. And finally, the last topic in instrumentation is the cryogenic. And here I would like to remark the agreement of license with between Fractal and ISO to produce manufacturing the technology of the continuous flow cryostat. And like those that are working in most of instrument in the ISO in Chile, like those in Muse on the picture, and we have received training together François Lisson in ISO, and other services that offers Fractal are training courses, specialized courses at the different levels, general courses or custom courses that can be given at the customer site or in Madrid. And we range different topics from the planning, instrumentation in different levels of optics, and detectors and software. You can see here some of our customers at the moment, and now other topic or another service that offers Fractal is focused on software, developing pipelines or web tools or analysis tools for reducing, analyzing data, and especially working on database for several web pages. And Fractal has been working actively in the Hi-Fi, ensuring for the telescope Herschel, and in the pipeline of Hawkeye. Here you can see, for example, the quick look of Hi-Fi for Herschel. Another example is the Megara Fiber Moss assignment tool. And Fractal has, of course, developed its own suites orientated basically to the process of the management and the scientific engineering, where you can have a control and tracking all the whole project, the documents, the different version, new version, who has changes something in the project, in all the branches of that covers the system engineering. And these Fractal suites can be offered by hosting in our facilities, or can be bought or sold to the customer literally. We have developed several web pages offering several web tools for databases on Java and different languages, and like those on Estallidos or other research centers. And finally, well, I would like to talk about our observatory that we have in Guadarrama, where we have a 20-25 centimeters telescope, and where we can perform several tests in small cameras or spectrographs. So that's all.
For one question, please.
Isma, where is exactly the small telescope in Singapore?
In a very nice chalet that has Marisa and Pedro near Guadarrama. No, it's not exactly in the Sierra Guadarrama, but it's in their own facilities.
So let's thank again Ismael. The next speaker is John Manuel Casata from the big Spanish company Calar.
¿Tú estás en un pendrive? Sí. El azul. Yo creo que está la mía y la de la silla. ¿Están las dos? Ah, el PDF lo tiene. Está. Ah, pues fenómeno. Porque entonces no necesito. Genial.
En ese pendrive está la siguiente.
Y ya estás ahí. ¿Y cómo paso por aquí? Con esto, sí. Vale, no, esto es el proyector. Vale, lo necesito el láser. Ah, vale. Pues
Okay, good morning. My name is Joan Manuel Casalta from the company CENER. I'd like to thank you, the committee, for the invitation. For us, it's really interesting to know about your plans on science and instrumentation, and hope it's interesting for you what the industry can do in this instrumentation. So this is the purpose of my presentation, to show you what are the capabilities of CENER in scientific instrumentation. So what we show you some aspects of what we have done on the past. One slide about what we do at CENER. CENER is the largest private engineering company in Spain. So we are different fields on engineering. So we are in aerospace, you will see a lot of examples, but we are also in infrastructures and transport. So we do a lot of work on high velocity train in Spain, that now we are in UK, we are in United States. So it's a good business for us. Most of the business are in power and process plants, and the original business of the family in Bilbao was to build boats, and now we have a cut to help our customers to build boats. So it's a complete view of what CENER doing nowadays, but it's a a detail on what we are doing on space and ground astronomy and instrumentation. So we have different places in Spain where this activity has been done. So the headquarters is in Bilbao, in Las Arenas. So there it's more or less focused on mechanical engineering and project management for space projects. In Tres Cantos is the largest place of this activity in Madrid, and our optics engineers are placed there. So you need optical support. You will see some examples you can find there. Control of telescope, control of satellites on orbit. Also, this activity is done there, and part of control electronics is done in Tres Cantos. And in the place in Cerdanyola, nearby Barcelona, so we are building payloads for microgravity, for life science support. We also work on power electronics, and on ground astronomy projects are usually led by our people in Cerdanyola with the help of mechanical and optic people in Madrid and Bilbao. And we have different electronic labs, clean rooms, and integration centers that I will not go in detail. I prefer to show you these details. So CENER is really recognized by the capability to do complex mechatronics components, equipments, and systems. Some examples is that, well, this one on the top, this is the antenna. It's working in Curiosity rover in Mars. So for the GPL, we made the mechanism to move this antenna. So this a critical system working in Mars, and is doing really good pictures that have been sent from Mars to the Earth. So we are recognized for cluster booms done in different missions, in Solar Orbiter now, but in the past in Rosetta in different missions. We are quite active in Earth observation, so this is Sentinel-2 calibration mechanism, and this is for MTG. This is a complex and quite precise scanner system. I have seen on some of your presentations that you need sometimes mechanisms with really good stability. This is a good example. You will see later on with a test setup that we have built to measure the performances of this. It's a scanner that will be included in Meteosat third generation. This is not a satellite that has not been yet. And some example of exploration in landing legs for Aurora, but now we are working also in ExoMars mission. This is for space mechatronics, but we have passed from mechatronics to complex systems. So one that we are really proud is, the mission Gaia. So the critical system that is the deployable sunship has been developed and built by CENER for Airbus. So this system was deployed after 30 minutes that the satellite was launched, and it's okay. It's now working and doing science on space. Now we are involved on different systems on Solar Orbiter, so the antennas, the feed-throughs, and deployable booms that are critical systems because, well, the temperature gradient between the part pointing to the sun and to the universe is really, really critical. And other antennas that we have done for Bepi Colombo, and now we are building for next missions like JUICE. But these capabilities are parallel, and the experience also in ground astronomy. For the part of mechanism, we started in the year 2000, thanks to the building of GTC. We had the opportunity to build really a complex system that is the M2 unit. So this is a tip-seal system. In fact, it's the largest that is working now on the telescope, and a high-precision hexapod that makes the alignment of the secondary and the primary mirror. So it's working for several years now on GTC. From that, we jumped to Vista telescope that is only between brackets and a high-precision hexapod moving a mirror of 240 kilos mass with precisions of microns. Some experience for IRAIT, a telescope in Antarctica. Some small production, 70 units for a robotic arm that are placed in front of the receivers of ALMA. And this is the last recent one. So this is a hardware. It's now on Astrophysics of Canarias. That is the focus translation system for the instrument width for the William Herschel telescope upgrade. You need to move a mass of 4.5 tons to 5 tons with precisions of 20 microns. So this system is already done with a record of 6 months and delivered to IAC to be installed in La Palma. And the last but not least, we delivered in 2010. This is the the M5 mirror field stabilization unit for the ELT. So, well, the ELT is really big. The M5 is 3 meters elliptical mirror, 3 to 2.5, and it's heavy about 400 kilos. So we're doing the field stabilization with this large mirror with a bandwidth of 10 Hertz and having really good performances. This is scale 1 performances. It's at ISO premises. If you are there, you will see this high one. This is a good example of tilt system that we can scale, we can do it larger, smaller, and include it in part of your instrumentation. Now I pass to the experience on optical systems and instrumentation, that it's also wide and different. First, some examples of our capabilities in optical design. So our group of optical engineers can do design of wide angle lens, so slitting systems, infrared systems. This is according our experience done in different projects, but also in imaging spectrograph development, so as snapshot spectrometer and spectral imaging cameras for industrial and astronomical applications. Sometimes these are internal developments, so part close to the 15% of the money we earn we devote to internal research and development in fields that we understand that are really interesting for us in the future and for our customers. This is also an interesting mission. It's the first time that a Spanish company it's leading a mission for ESA. So we are leading mission PROBA 3, that it's make a flight formation of two satellites. This is really interesting for the future because, well, instead to put a large James Webb Space Telescope in one satellite, you put different mirrors in different satellites, you can align and fly information, and you can build really larger telescopes on the space. So we are doing all the part of control of these satellites, but we also are doing studies of straight light analysis for different instruments that we are doing in this demonstration mission. This is under development, but we will fly it soon. Have the time, maybe 2-3 years from now. Other good example of capabilities of Spanish industry in optics is that we are the prime contractor for payload, the main payload of the Spanish Earth observation satellite. In fact, it's a telescope pointing to the Earth. It's a complex telescope. We have a GSD of 2.5 meters and with a swap of 60 kilometers. Really, it's a complex system. Maybe you can have better 0.5 meter resolution instruments now on the market, but the swap of 60 kilometers is making this telescope really difficult. So now we are mixing scientists' requirements with industry requirements for this Earth observation, and well, now it's already aligned at Thales France facilities, and hope that to be delivered by the end of next year. And we have been responsible of all the optical design, system engineering, and integration of the system. Other good example of optical design is this camera. It's a camera made for the World Space Observatory. It's in ultraviolet. So it's the camera called ISIS. In that case, we performed the design up to PDR, but the project finally was cancelled due to the lack of budget during last years. That has been not easy for everybody. But the design is there. It's the design on ultraviolet field, and the experience is in our side. Other experience, we usually participate in the first parts, and according to the customer, they prefer to continue. In that case, for INTA, we participate in the Raman spectrometer definition for ExoMars mission. On ExoMars, we have other systems like the drill and deployable solar panels, and also a collaboration for an instrument with the RIA. Other good examples on optics, we have capabilities on optical design, but also later on we need to verify the performances of the systems. So in the system I showed you before, now it's the hardware is already built. We need to make a test setup to measure the accuracy. In that case, we have 20 nanoradians with a range of ±10 degrees. So we need to measure this accurate, and we build our own optical setups to measure this performance. On other side, what other participations in instrumentation? So this is also a good example of critical electronics we are capable to do. In fact, it's the data management unit. It's the part of digital control of the main payload. In fact, it's a unique payload for the LISA Pathfinder. This is a project made for EEC, and we were responsible of all the parts, all the different boards and radiation monitor, from the data acquisition to the power and to the transfer information, interface information between the main payload and the spacecraft. Well, this mission already flown and got really good results. Other good example is done for Astrophysics of Andalucía. It's the project SOFI. It's for the FEE instrument in solar orbiter mission. We are participating in different boards and even in the correlator tracker camera for the stabilization of this instrument. In fact, this hardware is now on flight model phase, and now we are running really hard to achieve the dates to deliver the hardware. Compared to the mechanism, we have also participated, and it's our interest to continue on that market on ground astronomy instruments. For OSIRIS, well, when you have a telescope large like GTC, the instruments become larger. So the filter wheels were around 1 meter, and the heaviest wheel, with greens and to enable filters, was around 100 kilos. But the gravity deformations of this large wheel were really critical. It's about 14 microradians deformation that we should achieve with this mechanism working on the instrument. Well, the instrument, as you know, it's installed and doing science. Another recent experience has been on the part of cryogenics. So we have participated with different companies in Europe in the DTU, that is the detector translation unit. So in that case, we provided the cabling and electronics for CSEM, a Switzerland company, and for the CSU is the configuration slit mass unit, 110 bars that are present in the field of view with a really good repellability. In fact, this is the spec, but the repellability achieved with these bars are around 2 microns, so a really good performance. So all the electronics for these piezo actuators are done by us with a special cards and a special cooling system on the rack. Another good experience is with ISO. It's for the upgrade of one of the telescopes with laser guide, natural guide stars and laser guide stars. We made the GRAL detailed design and implementation. It's a co-rotator. In fact, it's placed in front of the Hawkeye instrument, and we place the wavefront sensors in the field of view to get the information from the lasers and make the corrections on the secondary that is now being installed. So this hardware is now in Paranal, and it's already been commissioned by our customer ISO on the telescope. And it's another interesting experience for us has been for Carmenes. So we put our small contribution there. We made for the IAC the preliminary and detailed design of the cross disperser, the greens and the exposure meters. So these two systems you see here on CAD and on measurement on that case, on the final configuration. Well, maybe not the final. And some support at the end before CDR for RIA and the collimator fiber exit unit, mainly on the 3D model design. And my last slide, it's also related to front-end electronics. So some of you have talked a lot detectors. So take into account that we are capable to integrate these detectors, do the front-end electronics. This is experience for microvolometer detector for infrared observation. Or another example is large CCD cameras for for photogrammetry applications in Argon. So this is all on my side, just to give a rough idea about our capabilities, and anything that we may help you, we are open to discuss. Thank you.
Questions?
Do you feel that now there are less instruments being built than in previous years?
Are you talking on space?
In Spain.
In Spain. Yes, I think that the start of GTC makes a first step. It was Osiris and Emir. Now you have really a good experience on Megara. And well, I think the opportunity right now it's on the ELT. I'm afraid we did not achieve the time to lead one of these instruments. I understand it's really quite complex, and now we have to push on the track of ELT instruments. Most of the activity will be there. But it's true, well, you know better than me what is the program on GTC, that possible for a telescope of this class would need more upgrade. But finally, the finance are what they are, and okay, we need to adapt to that. We are after you on that activities, so it's our own interest to have more instrumentation. That's the reason we are here, and on Calar Alto, on La Palma, or on ELT.
More questions? That's all. So let's finish again. The next speaker is Calar, the proactive R&D company.
Tu charla estaba en el...
Es la que es el PDF. Sí.
Es un PDF.
Sí. ¿Cuál es el enlace?
Espera, un momentito.
Sí.
El láser es el botón rojo.
Esto.
Sí.
Vale. Okay. So hello, my name is Juan Herranz. I belong to the company Proactive R&D, and in this short presentation I will try to show you the contribution we had in the project Cármenes, working for the Institute of Astrophysics of Andalusia. I try to be focused mainly in technical issues, but since the time is short, maybe if you have questions afterwards, we can discuss it. So in this presentation I will try to show a very brief description about the Carmen instrument and the work we perform for the optical band supporting system, as well as the optimization of the cooling system design. From the optomechanical point of view, we make the final design and the procurement of the fiber exit unit and the shell mount, and then a little summary on the contribution in Cármenes, and finally I will show you the scope of our company. The cryostat of Cármenes is a vacuum tank, 3.5 meters long and 1.5 meters of diameter. Inside this vacuum tank we have an optical bench. On top of this optical bench we have all the optomechanical equipment of the instrument, and around this, between the vacuum tank and the optical bench, we have a radiation shield who is in charge of avoiding radiation to reach the optical bench. So somehow the red circles try to show the parts of the project where we have been collaborating. The challenge in the case of this cryostat was to minimize the thermal flux, because the Calar Alto facility have limited power cooling. So to have a very low gradient in the optical bench. Also, the fact that we have important thermal contraction between the optical bench and the supporting system, because the optical bench is a cryogenic temperature, the supporting was a room temperature. And one important point was the fact that we had to maximize the natural frequency of this optical bench. The final performance of this cryostat, the working temperature is 140 kelvins. The total radiation flux we managed to have like 16 watts and 2 watts 2 watts coming from conduction through the supporting system. And the final natural frequency we achieve is in the range of 17 Hz. So the supporting system of the optical vents, the particularities of this system is that we have a massive optical vents that is 650 kilograms that has been supported in three G10 isolation feet. And the challenge here was to absorb this important contraction because these feeds were supported in a frame that was at room temperature, while the optical vents and the radiation shield were at cryogenic temperature. So one of the solutions we used in order to increase the stiffness of the system consists in using a rigid element between two of the three feet, and this rigid element could not absorb the thermal contraction between the cool and the hot part. However, what the solution we found is to provide a preload in the warm configuration in such a way that when the system is cold, this preload pass through a zero and come to the opposite somehow direction, and like that we managed to divide the stress, the normal stress we will have in these feeds by 2. And this was the conceptual model, and then we make different finite elements analysis to verify that the stress was in the acceptable limits. And other solution we found to maximize the natural frequency of this massive bench was the installation of the sliders that allows the contraction of the bench in a somehow smart configuration that allows the system to contract in this direction. However, they don't include additional degrees of freedom on the system. With these two solutions, we managed to find 70 Hz of the first mode of natural frequency for this bench, which is quite good if we consider that the mass of the bench is 650 kilograms and is supported in G10, that is quite flexible material. Now I would like to move to the cooling system optimization. This shows the radiation shield. Inside here we have the optical vents and all the optomechanic system. The particularity of this shield is that it's cooled through different heat exchangers, and this heat exchanger, they haven't any kind of regulation, individual regulation. So in order to optimize the gradient in the system, the only solution we had is to optimize the geometrical position of this heat exchanger. And another question or another challenge was that this heat exchanger was somehow coupled 2 by 2 in the cooling lines. So that is a challenge in order to optimize this configuration. And one important challenge was the fact that we were working with very low emissivity values, which makes the calculation quite difficult in terms of convergence of the solvents. So the model that we decided to use to modelize this system and to optimize the position of the heaters, of the coolers, was to make like two different finite elements analysis. One that we calculate the heat load coming from radiation from the base cell, from the vacuum tank to the radiation shield. The results of this heat load we apply in a second model where we have only the shield in the vents and the system, the supporting system. And from this model is where we optimize the position of these heat exchangers, and also we finally evaluate the gradient, the thermal gradient in the optical vents. So somehow this strategy was used in order to make the model more simple for the calculation. Here is typical results that we could find in the temperature distribution in the radiation shield, that the gradient is in the range of 2.5 kelvins, and here is the results of the model for the thermal distribution or the thermal gradient in the optical vents, that is in the range of the 10th of millikelvin. So this is concerning the cooling system optimization. Now I would like to move to another part of the project where we've been in charge, is for the final design and the procurement of the fiber exit unit. The particularity of this system is that this is a quite small device that have requirement of optical resolution quite important, in the range of 5 microns, and also from the angular resolution in the range of 250 microradians. Also the fact that this system was working at cryogenic temperature, and maybe one important challenge was the fact that this system had to be commissioned at different temperatures. At warm temperature, at something we call warm ambient temperature. This configuration was warm temperature, but with some spatcher we managed to make the system optically coherent. And finally, the system was working at cold temperature. So in order to move from this to this, we had to remove some elements that were simulating the thermal contraction. So this was an important challenge due to this level of resolution, especially in the production of this device. Here we can see how looks the final device that we produce in the area of Barcelona. And we integrate in our own facilities. This production of this device involves high precision machining, thermal aging, because these aluminiums that are working in cryogenic temperatures, they have to, we provide a thermal aging process in order to avoid the formation in the device when it's in cold. We also apply a mineral black anodization, and then finally this device is vacuum compatible. So this was also one of the features of this device. And here I just would like to show very briefly two of the most interesting features. This is a little chariot that is used to align two of the fiber, the science fiber and the calibration fibers. With a very high resolution, this system allows to position both fibers respect to the rest of the optical elements, and also provide individual alignment of these two fibers. This device is quite challenging from the design point of view, but also from the manufacturing point of view, because it's quite small, and we are just dealing with very thin silicon fibers. Another interesting feature in this device is the pinhole mask that was located between the optical fibers and the lensed barrel. And this pinhole mask is a 200 micron pinhole mask that is it's not very clear shown here, but the tolerances were quite narrow. And all that has been produced in the home internally. This is another optomechanical mount that we've been in charge for the final design and the procurement. This is the shell mount. The particularity of this mount is that this is housing a massive optical element. This is the shell. The shell was like a 35 kilograms, and the requirement was a very high stability, and as we have to support this flat element, in the machining of this mount, we were considering flatness in the range of the 10th of micron. So in this case, I would like to profit to show the process of production of this mount. We make a pre-machining. After this pre-machining, we perform a cryogenic aging, just in order to avoid future deformations in the material due to the thermal effects. We make a final machining, then this mineral anodization, that is somehow the organic anodization is quite trivial, but the mineral anodization needs a bit more of a test. And finally, we perform a real final machining on 6 spots in this holder. 3 of them were to support the system through the optical lens, and the other 3 that are in the other side of this picture were in order to support the mirror. And then we also participate here with the people of the RIA, the Institute of Astrophysics, in the integration of this of the optical mirror in the mount. In that case, it's not the optical mirror. This is just a dummy that we were using just for the commissioning, for the test commissioning, or for the training on the mounting of this optical element. So as a little summary, what we have provided for Carmenes, we were working in Carmenes since 2011, and we, as you could see in the presentation, we were in charge of the final design of the shell. For the fiber AC unit, we were also in charge of the final design for the folding mirror. We performed also for the folding mirror some thermal stress calculation in the optics in order to evaluate the possible stress due to the positioning of this mirror. We performed the optimization of the cooling system, and also from the collimator we performed some thermostructural analysis in order to evaluate the stress and the deformation and also motions in the collimator and the mount of this collimator. In addition, we provide other smaller optical elements and also sometimes even small mechanical parts, because these guys in the Institute of Astrophysics here, they were quite busy, and our goal was always to provide them with the maximum support in order they could still continue working in the project. So, in case you would like to have more reference about the company, you can contact Pedro Amado, who is the principal investigator for the project, Santiago Becerril, who is the responsible for the mechanical engineering, and Conchi Cárdenas, that unfortunately is not here anymore, but she was responsible for the optical part of the project. So finally, in this slide, I would like to show you briefly the scope of the company or what we can do. In proactive R&D, we can do high precision mechanics, we can perform optomechanics, we know how to work in ultra high vacuum environments, we can perform cryogenic design, we can of course perform stress and thermal calculation, always analytical by finite element methods. We know how to deal with special materials. We can perform manufacturing follow-up, integration, test, and commissioning. In the area of Sabadell, we have an integration area and some machining workshop where we can produce equipment. Typically, how we do is depending on the size of the precision required. Sometimes we make in-house, or sometimes we can make with subcontractors in the area. And the final integration we always perform in our own facilities. In addition, we have some key partners for projects. So depending if, for example, we are a small company, but sometimes if the project becomes larger, we are always able to find a good partner for you to continue in the project. So we have other, concerning the software tools we have, we can use ANSYS, MATLAB or MATCAD for analysis or calculation, and from the point of view of design, we typically use SolidWorks, more recently now, and Inventor, and we can also use CATIA. And maybe the more important tools we have is a high degree of motivation. We try to be extremely flexible, especially working in this kind of environment where the project needs a lot of flexibility. We are flexible not only from the technical point of view, also from the financial point of view. We try to be flexible. For the timing, we try to be flexible to adapt to your needs. And maybe the most important thing we have is that we are proactive. We are proactive in the sense that we don't want to stay, or we don't look to stay just in the pure requirement. If we find that we can bring something to you, or you discover something during the process that could be interesting for you, even if sometimes that means that we have to work a bit more or something like that, we are always open to communicate you or to propose solutions or to propose improvements. Because when we are working in something, sometimes the customer cannot see the detail of the project, but it doesn't mean the fact that we collaborate together that you will lose the contact with the detail of the project. We try to always provide you with this information. So I think here is some of the customers. Of course, the Institute of Astrophysics Andalucía. We also provide some equipment for Calar Alto, for Astrophysics of Canarias. Myself, I am coming from the field of accelerator physics, so I used to work with CERN, with ESRF, that this is like SUS in France, in Grenoble, also with ALBA, that is the only synchrotron we have already in Spain, CMAT, that is also in the field of accelerators. Also, we collaborate with universities. For example, we provide some equipment for University of Zaragoza. This is another laboratory of CSIC in Madrid, and we also have experience. So we've been working with. This is a medical company. So somehow this is what I would like to show you. Well, I would like to say thanks especially to the team of Carmenes NIR in IAA, because it was a pleasure to collaborate with them. Also, I am happy that this project is going ahead, and also I would like to thank the organizer for this opportunity to show what we can do. So that's all. Okay.
How immediately could you accept a project? I mean, the volume of work you have is how high?
It depends on the size of the project, but in general we are very flexible organization. So for example, for Carmenes, for some project we provide support in 2 weeks. And even less if it's the case. Yeah.
Very short comment.
Yeah.
Half of Carmenes, you did a very good job.
Thank you. Yeah. Welcome.
The speaker is David Barrado, now to the European.
Era David, 2016 se llama.
Sí, empieza en
Vale. Aquí me dice actualizar vínculos.
No queda.
Que
no
no,
se puede.
cancelar.
Sí.
Vale.
So my talk has 2 different parts. The first is just science, and I have prepared this thing with the Nuria Wellamon and Edwin, and now he's in Bordeaux. And I'm going to tell you what we need in order to be able to elaborate a new age scale for different astrophysical phenomena. But then we will try to use different instruments at Calar Alto now, and we believe also that we need, and also Calar Alto needs, and the community, to give a quantum leap, and I will reformulate an old proposal. So what is Chronos? Why now? Actually, age is a very fundamental parameter for the description of any astronomical object or phenomenon. And actually, although we are not aware of it because we prefer to ignore, because the problem is not easy to tackle, there are very strong discrepancies between ages. For instance, in the case of stars in a cluster, when we use different methodologies, up to 50%. And in fact, for instance, we have clusters, lunar clusters, that they seem to be older than the universe. And this is a very important problem that we are not trying to solve. Anyway, there are many reasons why we are in this stage. But essentially it's because there is not a systematic way, a robust way to calibrate different methodologies. And our goal is to try to deliver these universal self-consistent absolute, because there are also relative age scales, and accurate for the entire time domain. So this is just an example of the actual situation. I have a collection here of different clusters and 2 different methodologies. The standard methodology using isochrons fitting for clusters of different ages, and the lithium age that in principle is very simple, although it cannot be applied universally because it also works for an age range between essentially 20 and 400 million years. But the point is that when we apply it to the same cluster, in few cases they are similar. Well, it doesn't work very well. Few cases they are not very different, but in other cases the Pleiades probably is the best well-known cluster. There are just in the last 5 years, like, I don't know, 500 papers on the Pleiades. Still, we don't know the age. And this is a fundamental reference for all the astrophysical we know, not only in stellar physics and stellar astrophysics, but also up to cosmology, because we have not only a distance scale using different candles. We have been building within the last 100 years also this age scale that is not auto-consistent. It's a very messy business. Anyway, different phenomena, you have here a collection of them, depends on this scale. And the bottom line here, we only have two anchors. We only know two different ages in the universe. One of them is the age of the sun, and the other one is the age of the universe, if you believe in cosmology. And they're on top of here in this diagram, and this is a logarithm scale. Anything that is here depends on models, depends on data, depends on different things, and this is not consistent. So the goal is to try to have a look in a consistent way and to do it properly from the beginning. I don't know whether you have played this game called the Jenga, that is these pieces of wood, and you are building a tower, and you pick up one of them and put on top of it. So eventually the tower becomes unstable and collapses. So you need to do it again. And this is the point where we are. We want to rebuild this thing. This is a collection of different methodologies that we want to have a new critical look at them. Lithium evolution in cluster stars, for instance, isochrone fitting, gyrochronology, stellar activity, kinematic, etc. There are a collection of them. Some of them can be applied for different masses, for different ages, but nobody has tried to do it from a comprehensive point of view. So essentially, this is the scheme that we want to achieve. This is the age, the different steps where we want to use in order to have a look and to actually build in this coherent way. The lithium depletion boundary using DANCE. DANCE is an ongoing optical survey that is providing very nice, clean samples of members in clusters of different ages. Then there are other methodologies that they can apply to different ages. So there is a loop of auto-consistency to try to produce this absolute age scale. Here, the key line is to have very good spectroscopy. So Chronos and the role of Calar Alto now is to supply this new data, essentially, as I say, high quality, massive spectroscopy, also some data with the absolute in order to characterize visual binaries, because we want to do this, as I said, in a comprehensive perspective. So our aim is to try to get to convince eventually, if there is a proposal, a call for big project, these 200 nights in order to exploit, essentially it would be with CAFE but also with Carmenes, in order to provide this huge database and to do the work. But in any case, we believe that there is a future role, because this goes much further than our aim. The massive spectroscopy is a need by the community, has been recognized by different key documents by the European community. Also the Americans have similar studies. The need of a wide field, wide quality spectroscopy is a demand. And there are several scientific cases that can benefit, not only the field of astrophysics for cluster stars, but also you have here a collection of them, And also because we are producing now and in the near future a massive photometric surveys that they are going to produce hundreds of thousands, millions, tens of millions of objects that they will require this spectroscopy. So this is an old and updated, actually, diagram. What is happening now at Calar Alto, what is going to happen in 2018 plus. Calar Alto is an excellent place to do spectroscopy, has been proved, is an objective statement. In the past, dedicated telescope, a 6.5 meter telescope, was proposed to do this spectroscopic cartography. Now I have changed the name to Telescopio para Cartografiados Espectroscópicos. Why we believe that is a niche? Because here you have a collection of instruments and telescopes. From here up there is a 4 class meter telescopes. From here is instrumentation in 8 class meter telescopes. For chemical analysis and for radial velocities analysis, essentially the accuracy, the error you are going to get is a function of the spectral coverage, the signal to noise ratio, and the resolution. I'm not going to go into details. Some of these instruments have a very nice multiplexing, but they lack either the spectral coverage or the resolution. So there is always a trade-off how you design your instrument in order to achieve your science. 4 years ago, we had an idea about why to build EXA and what were the scientific goals, the cases that could cover with different kind of instrumental requirements. So I'm not going to go into the details. Actually, we had a meeting here 4 years ago to discuss these science cases and this possible instrumentation. The bottom line here is that EXA was approved by Mineco at that time, but the RIA, they were a very positive report about the need of the telescope and instrumentation. This is an overview of what was EXA. Was a 6.5 meter telescope with the goal was the field of view 1.5 degrees. The multiplexing, the bottom line was 500 fibers. And as I said before, there are several scientific cases that we had in mind in order to optimize the design of the telescope and the instrumentation. Some additional details about it, but I'm going to skip this. This EXA, already you have seen this morning a design that we did, a conceptual design with the together fractal and the telescope. Several of the instrumental concepts that we had in mind. One of the points is how you allocate how you get the light from the focus. In this particular case, we have a fiber positioner called EKT. We have a multifiber spectrograph. Also, the concept of IFU, a camera, and in the second last meet, we also have other kind of instrumentation. These things were at the conceptual design, as I said. In the case of EKT, to pick up the light with the fiber positioner, this is the design. Here is more detailed, some details about how it would work with the fiber positioners, how one of these positioners, or several of them, could go not only to a medium resolution spectrograph, but to a camera, to a cafe-like shelf spectrograph, or to a IFU unit, or several of them, because it depends on how much money you want to spend. What happened with EXA? So we passed the conceptual design. We were going to go into the preliminary design. We put a proposal for the Junta de Andalucía. The crisis came, the project was stopped. But as I said, we followed the roadmap for infrastructure of the ministry, and EXA never obtained a negative report, was always positive. So now, we want to do this very detailed spectral characterization, trying to go for the largest, at least from a science justification, to go to the best possible spectral resolution, like 40,000 or even larger. For the spectroscopy, we want a very high signal-to-noise ratio. This is one of the reasons, for instance, when we study lithium, we have very weak features. Also in the H-alpha, there is structure. It gives you information about what is going on when the light is formed. Even for M dwarfs, that is the case of Carmenes, many things that you see here, this is the lithium line, there are several bands, but many things that you see here is not noise. Actually, there is a lot of information, chemical information in the M dwarfs. So you need to have high spectral resolution, have high signal-to-noise ratio to be able to really get the best out of your data. There are several possibilities in order to get this high spectral resolution and multi-object or wide field data. This is one of the proposals that was included, and actually Jorge yesterday discussed now the same kind of proposal for the 3.5 and 2.2, is to use the Fourier transform spectrometer in order to get essentially data cubes with all the spectral and the spatial information. One of the references that we had in mind at the time was an instrument like IMAX in the Magellan telescope. This plate where you cut the slits, so you have to know, I mean, any single slit, any single plate is unique for any plate. This is a field that has IMAX. This is the spectra that produces. So it's customized for the fields, and it can be only used once. But there are problems with this kind of design because actually, if you have an object close to the edges, like here, the spectrum will be here, so you need a much larger detector in order to get it. But there's also confusion. There is a limitation on the resolution. There is several problems. It's not optimal. If you go to a design like a cross dispersed shell, like you put many cafes, for instance, you need to have. It would be wonderful, but you need to have a lot of detectors. For instance, a fiber would go would pick up the light and would go to any to the single spectrographs and to the detectors. The problem that is when you have, for instance, a multiplexing of 300, then the cost is multiplying. So I like this kind of design. Hermes is in the Australian telescope, where you have different channels, and the channels are optimized for the specific spectral range. So you don't have everything, you don't have the complete spectral coverage, you just select simultaneously those spectral ranges that are interesting for your science. So I really like this kind of design. I was talking to Martin this morning. There are now new ideas, there are new possibilities. I am just giving you some insight of different possibilities, but there are new things that could be in place. Actually, if you remember, a few months ago, Tim de Sus, in the Spanish Astronomical Society meeting in Bilbao, was telling us that the next challenge is to have a dedicated big telescope, and he was talking about a 12, 15 meter telescope, and actually is what I was thinking of, to produce this massive spectroscopy, high quality, high spectral resolution. And although EXA was a very promising concept and was stopped, still I think that there is a lot of room, there is a lot of space and niche, and we have the capability to do it, so we only need to accept this challenge and to go on with a project like this. There are several possible collaborations, and this is an international need that is not being covered so far, and this is a kind of business where the first to arrive is the one that takes all the credit and all the benefits. In any case, I am presenting here, just to summarize, this cartographic project for Calar Alto with the current instrumentation, but also I would like to, again, throw into the floor this new challenge. So I believe that the Spanish community can take it and to still go on with this very ambitious project and to take the lead and to produce wonderful science. So thank you very much.
When you're talking about this 200 night observation, is with the present instrumentation?
Yeah.
But it's some kind of long program, or?
If one of the goals of this workshop, as far as I understand, is to try to use, to think about big programs for Calar Alto. So the intense use of the current instrumentations. If eventually they make a call, it doesn't depend on me, of course. But if a call is made, I would be ready to put a proposal for 200 nights.
Well, I think that this is really a very big challenge for the future. Of course, well, considering the current situation, of course, this is going to be very hard in case that the projects go ahead. But in any case, my question is regarding, do you have any input about potential international collaborators?
There is a list there. Possibly just it's a speculation. I didn't. It's not my role to talk about Calar Alto at this level. I'm just a scientist.
Well, I don't catch the design of the primary mirror. It's a 6 meter. One part. It's a
monolithic.
Part. It's monolithic.
Originally, exact. The design that was done 4 years ago was monolithic. Yeah.
Do you identify partners? Because I understand in the United States they have the capability to do the 6 meters mirror, maybe the unique, not in Europe.
Actually, at that moment, we had the chance to collaborate both with Mexico and with Arizona because they had a blank. That is the one that actually, if I am correct, is the one that is going to San Pedro Martir. So at that time, we had the window because it was there, the blank.
GNP, so they have some of them. So could be another one.
Now that we are thinking that if we go forward, then we will have a critical examination of the size of the primary mirror. I think that we have to be more ambitious, and then it's not going to be monolithic. Probably, but it depends. The feasibility study is meant for this kind of radius. What is the actual scientific needs and what kind of telescope and instrumentation are needed to comply with them, to achieve the goals.
Thanks again. Our next speaker, if we don't have a big technical issue, should be Jianmin from China.
Perdón, tú pásame el micro, el altavoz, tienes que poner el micro. Sí, sí. A ver, este señor. Sí, claro, ya le voy a llamar. Vale, ya le estoy llamando.
Yo ya puse solo con uno.
Hi, Yanmin. Can you hear me? Can you hear me? Pero esto... ¿Se escucha?
Está escribiendo, pero very clear. Él sí te escucha, pero aquí no.
Yes, I can.
Okay.
I can hear you.
So we are.
Can you hear me?
Yes, we can hear you.
Okay, fine.
So the audience is ready. So
Yes,
when you want, you can start.
yes, I can start now.
Yeah.
Okay.
Yes.
Hello everyone. I'm Jimmy Wang from Beijing. I'm sorry I'm not able to attend the interesting workshop in Spain, but simply due to some U.S. Embassy visa application problems. So so I have to give the talk through the Skype. I'm going to talk about the reverse mapping of the map. In optical.
We have problems.
Which are really a fashionable subject in the astronomy now. So the reverberation mapping is not a new idea, which basically looking for the emission line, especially broad line response to the varying continuum to measure the time lag and then get the structure of broad lines and then fix the structures. Oh, sorry, next. Sorry, next, maybe page 3, okay.
Yeah.
Sorry, so in 30 years ago, basically the reversion mapping is only for the kinematics and the structure of broadline regions. So with the great efforts in the last 30 years, so the people have done for roughly 50 AGNs to set up the well-known RL relation I show here. They are on the left side. This is very tight RL relation for black hole mass estimation for AGN, which is very similar for the dynamical method to determine the black hole mass in the normal galaxy. But we have to assume the broadline region is visualized. So the RA relation paper have very, very strong impact. Now the citation is roughly 1,300 since 2000. So it's very, very important and fundamental in AGN research. But the question is the base of the RA relation, So next, so is the base of the RA relation so solid? I think the answer is not yes. Okay, I cannot say no, but the answer should be not yes. Okay, to see the famous object NGC 5540 that's in the middle panel, the RA relation is very different from the statistics of the sample. So what is so there must be some outliers even in bands 2013 there are already 2 outliers in the RL plots. So what we can do with the next page? So the people apply the RA relation for all of the quasars. They also extend the RL relation for H beta to the line of magnesium 2 and carbon 4. So they get estimate of black hole mass for all of the Sloan quasars. Even to estimate the black hole mass next. Even black hole mass in the highest redshift quasars at redshift 7. So this is the spectrum of the highest quasar. So next. So what we can do now with the RL with the real version mapping, I think we can do with the 4 aspects for black hole through the measurements of black hole. Firstly, for the co-evolution with the host galaxy. Second, for the black hole spin, and for high-Z cosmology. Probably we can find the supermassive black hole boundary for gravitational wave. I will briefly talk about this next. So the two plots show the very famous co-evolution galaxy, black hole galaxy relation in the so-called, this is so-called the Margot relation and the M sigma relation, but this relation only sets up a connection between the mass, the black hole mass and the galaxy bulge mass. The very obvious question is, how about the spin? Does the black hole spin related with the host galaxy or not? So we set up a so-called eta equation. Eta is the relative efficiency of the accreting black hole of the black holes. So this equation can tell us what the cosmological spin of the black holes if the co-evolution hold for all of the redshift. So the right side of the equation fully depends on the observable. The energy, the luminosity density, the U dot, which can be done from the luminosity function. We need the black hole, that mass density, which can be done from the RL relation for the large sample. So we have to employ the duty cycle, which can be done from the large survey, get the ratio of the active black hole to the total. So basically we can, if we get the three informations, we can get the black hole spin. Next, please. So this plot shows the relative efficiency is going down rapidly with the cosmic time. So this shows that the random accretion not only led to the growth, but also spin down the black hole. This simply implies the secular evolution, probably very important, or the minor mergers power the cosmic growth of the black hole in the centers. So how about from the numerical simulation, we can compare the two panel next, please. So multi-voluntary make the numerical simulation and exactly show the exact same number of the epsilon with the eta. So this means that if we get the better R relation to estimate the black hole mass, we can reliably estimate the black hole spin. Of course, the evolution of the evolution of the spin will be the one major of the task for the Athena, which is planned to be launched in 2012-8 through the K-alpha line profile. So this means that if we do the regression mapping for large sample, we can get the better R relation for black hole spin. Okay. So what is the next for cosmology? So basically, we are doing with the Chinese 2-meter telescope in Lijiang. So the supernovae cosmology now show very exciting results because the universe is expanding. But from this plot we show here, the supernovae is very hard to see, to detect for high-Z universe, especially for 1.5. But how about the detection of supernovae from the next generation of instrumentation? For example, even the JWST. Next, please, and the W first, they show the number of the supernovae, type 1 supernovae detected is very, very few, even less than number 10. So basically, the cosmic ladder could be broken, but how to extend the cosmic ladders? We suggest now we are doing with the Chinese, next, please, with the Chinese 2-meter telescope in Lijiang, the star is here. It's very too close to Tibet in the west southern China. So we are looking for the superheading the massive black hole to do for cosmology. What we can do, we start with the real version mapping to target, to select some target to do that, okay, according to the accuracy rate. Now, next, please. And then next, here it shows the typical spectrum of the superheading black hole from Sloan. The up panel is show the candidate of superheading the AGN. The below panel show the normal case. So we can see the spectrum very different in several aspects. So we do next, please. We do this with the long slit to put the target and the comparison star in one long slit for the calibration. So after 3 years, actually 4 years, sorry, next page, we detect about 30 objects, and we have 20 objects successful actually. So next, so I show you the light curve and the real variation in one example in our targets. So this clearly shows the time lag of H beta very easy to detect in this way. Okay, next, please. So our target already show the H beta lags is significantly shorter than the standard, than the well-known RL relation. This means that superheading black holes doesn't follow the RL relation. This is the latest result from our campaign. We can compare the 3 panel. We found this. So we can show more clear the deviation of the H beta lags strongly depends on the accuracy rate m dot. We show on the left panel. So we have to include the accuracy rate at the second parameter in the R relation. Okay. The next, what is the controlled H beta lags? Simply due to the anisotropic of the ionizing field when the accuracy rate is higher. So the inner part of the accretion disk will shadows the ionizing luminosity by themselves. So the broader region could be divided into 2 regions. One is the shadowed, see the left, okay? You see the right panel. So the shadow region and unshadow region. Now we detect the shadow region which has shortened H beta lags. But where is the longer lags? We have to detect. We have not detected yet. So another important result from a campaign, we show the saturated luminosity. So the left panel show from the very famous paper about the slim accretion disk by Abramovich 30 years ago almost. They show when the accretion is higher, the radiated luminosity tend to saturate it. This is very clear, but it's never been confirmed from observations. But our SimBeach collaboration published by Du et al. In this year, we show it's very clear their saturation. Okay, to see the red points get saturated in the right panel. What this is due to the famous photon trapping effect. So this makes the red luminosity saturated. This can be applied for cosmology. So this next, please. So this shows that the estimation from saturated luminosity for distance compare with the stand cosmological model. So the index, the accuracy of the black hole candle would be 1.5 dex, which comparable with the type 1 supernovae. So the fraction of superheading black holes increase with the redshift. So this is just the opposite to the type 1 supernovae. This is very easy to understand because the high redshift, they have the higher gas, so the accretion rate is easy to higher. Okay, next, please. So the lemma alpha forest BO measurements for cosmology already show the deviations, very significant deviation from the lambda CTM. This plot already show this, the red plot show here. So for the next 20 years, next please, this is the dark energy experiment arrangement in the scheduled in the US. We hope the superintendent black hole project can do something for the cosmology in next 5 years. Okay, next please. So finally, I will very briefly mention for the nanohertz gravitational wave. This is basically depends on the discovery of a supermassive black hole binaries with the really fashionable subject in the world. So next, please. So the very supermassive black hole binary will radiate the nanohertz the nanohertz gravitational wave. This show that. Please next. So through the PTA detection for the GW, we have to measure the time level of the pulsar to detect the gravitational wave. However, the 10 years detection next, please, from Australia is the field because basically we don't know where is the supermassive black hole binary. So this paper by Shannon last year showed the negative missing results. So that what's the reason is we don't know where is the supermassive black hole binary. Next, please. According to the hierarchical model of galaxy evolution, they must be there. But the question is, where are they? Next, please. So there are only 4 candidates. One is OJ 287, Macron 231, and PG 2130, and the last one NGC 5548. We show here, we suggest here in this year. So the figure now show, the picture showed a long tail for the NGC 5548. Okay, basically we folding the next, please, folding the H beta profile for the last 43 years. We get the red part, the red peak and the double peak. We get the the red peak and the blue peak are moving in the opposite way. This means that very similar to the normal star binary stars. So we show here this next piece. If we do the reversion mapping, we will detect there are 2 borderline regions. We develop multiple and inhomogeneous component analysis software, which is shortened by MICA, and we published this year to detect if there is a binary black hole. Show here. Next, please. So we need the telescope to do more, not only the Chinese telescope, but also from Calar, the 2-meter telescope and the 3.5-meter telescope. For if we have more time, we can make a progress in the last 3 subject. Okay. As a brief conclusion, the 2 and 3-meter telescope are still powerful tool for reverse mapping. We can do the black hole and host co-evolution. We can do for the high expansion of the universe through the black hole candle. We try to find the supermassive black hole binary. Thank you very much. That's all.
There's time for questions.
What would be the spectral resolution that you would optimally use for your measurements?
Can you hear? What would be the spectral resolution you would need for your measurements?
Sorry, I'm not very. The voice from you is not clear.
What would be the the spectral resolution you would need for your measurements?
Oh, it's one. So we only need the lower or intermediate resolution spectrograph. It's enough.
Okay.
More questions? No, that's fine.
How many nights?
Oh, how many nights would you need?
We need the whole year. So real version mapping is a very time consuming project. The Chinese telescope give us half of the entire time to us. So we need, for example, if we are lucky enough, we would like need the the 100% of the 2-meter telescope in Calar.
Okay.
Okay. So thanks again, Jianmin.
Last question.
Okay.
Frequency they need to measure the lines and the photometry. The spectroscopy and the photometry, because
Yeah.
this is crucial for
With which
copy and how many object targets they already have selected.
how many targets have you selected?
We already monitor 30 targets already in Chinese with Chinese telescope. We hope we can do 200 targets in the next 5 years. We have large project approved by the government, so we can. We hope to collaborate with Spanish astronomers to do this. I think the reversion mapping for black holes in galaxies, in active galaxies, still have a lot of opportunities to discover something new. Totally. Thank all of you.
Maybe one last question. Would a 1.2 telescope will be sufficient for your needs with a long slit spectrograph?
1.2 meter telescope is it's a little bit small, but we can do some very bright. We can monitor some very bright targets, but it probably need a longer time. Longer bright targets will need longer monitor period. For example, the famous paper by Caspi in 2000, they spend a 1 meter telescope in Weiss Observatory in Israel. They spend 7 years to monitor 20 PG quasars, which are really successful project in the last 10 years, I think.
Indeed, a bit long.
Yeah, a little bit long. Yes, too long.
So
yes.
Thanks again, Jianmin, for your talk.
Okay. Thank
you very much. I switch off.
Okay, so our next speaker is Antonio Necchi.
Of course,
¿Eso es un tuyo?
Son de Enrique.
¿En qué
Son del grupo. No, pero este lo estoy guardando yo.
¿En qué?
Lo estoy guardando yo. Yo lo llevo.
Es que conecta este también, por favor.
¿Esto qué va a hacer?
Sí, por darte energía.
Bueno, oops, sorry. Hello everybody, thank you for staying until the end, and thank you to the organizers for giving me the honor of having the last of the talks. So I'm going to speak about instrumentation for a quite different niche of science from what has been spoken until now. And it's the instrumentation for the follow-up and characterizations of transients, but not only, as you will see in a minute. So you know that in the next decade it will be the decade of the giants, the era of the giants, where we'll have the giant telescopes, we'll have massive surveys like LSST, CTF, well, JPAS will also be producing, and we'll have each night hundreds or even thousands of new targets that will be discovered, new objects, new very interesting objects in some cases, and of course we will need to have telescopes ready to take advantage of that opportunity, and there will be a lot of science there. So that science will cover many different topics, like from supernovae, X-ray binaries, gamma ray bursts, tidal disruption events, all these classical, explosive, very violent events. But not only, not only these ones we're discovering each time new different kinds of events that become very interesting, that become very first-line science. So it's important to be ready for that. The instrumentation that we are designing, however, is not only specific for this kind of thing. So we're thinking about instrumentation that can also serve as a pure workhorse instrumentation that can make a lot of people happy in the scientific community. So when we look at this follow-up of surveys and the study of these transient sources and such, we can make our wish list of the kind of instrument that we would like to have. So first, we want something that is fast, that is efficient, so that has basically no dead time between observations, that can be observing all night, that can produce a full night observations without spending almost any time or as little as possible in calibrations, in readouts, in whatever. As efficient as possible, both in optical and in quantum efficiency of the instrument, as operations. We are interested in both imaging and spectroscopy. We want very broad wavelength coverage, which has proven to be possible and to be very efficient for producing science. As we're studying as one of the major science cases, astronomical sources that evolve quickly in time, we want to have an instrument that can do reasonable time resolution. And of course, once we put things into the bag, we can ask for integral field spectroscopy also, we can ask for polarimetry, we can ask for other things, which would be maybe secondary for the main instrument, but that can give added information, added possibilities to do science. So, as a bit of historical view, the first of the first major of this kind of instruments that was built, covering many of these things that I mentioned before, was Octubre at the Very Large Telescope in Paranal in Chile. And this, as you probably all know, is that's supposed to be around 10,000, not 1,000, resolution spectrograph, which is a triple shell with 3 arms, an ultraviolet, visible, and infrared, with very good efficiency. Those of you who are used to shell spectrographs, having above 30% efficiency is very good. Well, we've been working already with this. I have a very tight relationship with this. It was part of my, I worked in this instrument during my thesis and also as a postdoc at the observatory. After using it for 7 years now, we know that it has some limitations that we would like to overcome. It has only visible light acquisition camera, which limits you the kind of science that you can do, especially for very extinguished objects, very high redshift objects you don't really see in the acquisition camera, so you need to observe it from somewhere else before. The acquisition is kind of slow. You need to realign the slits. This instrument has 3 slits, so you need to realign every time you observe. It has straight light from K-band. So there are things that we would like to improve. And following but it's been an extremely successful instrument, don't get me wrong. And I'm very proud of this instrument. As a follow-up of this Octubre experience, some of the people that participate in the building of this instrument are now proposing new instrumentation for smaller class telescopes, like the 2.5 knot, which is a telescope that has been doing a lot of transient science in the past. They have the Knot Transient Explorer being developed right now, which is a double shell spectrograph. It's similar to Octubre in design, although this one uses only one single slit and one single grating. They don't use dichroics to break the light, but a kind of a bit more intelligent way to do it with less optics. And they have a coverage in wavelength that only goes to H-band, which simplifies a lot the design of the instrument. It's foreseen to have 2 acquisition cameras, so we'll be solving the problem of the near-infrared acquisition, and the resolution is a little bit lower, as we also have a smaller telescope. It has an ADC and to correct the atmospheric dispersion in the full range. And well, the first lights was supposed to be in 2018. I think this is being delayed, as usually happens, sadly. There is another instrument that's following the similar scheme. We're also a little bit involved in this one, although less than we would like because there's little money for it. It's called SOX, that's son of Octubre, which was approved to be installed in the NTT in La Silla. This is a double shell again. This one does have two slits. The design is very similar to Octubre, just with 2 bands. Resolution around 4,500, with only visible acquisition, which is a pity, but I guess that's what you need when you need to reduce costs. I mean, if they manage to get enough money, they'll probably go for an infrared camera, but for the moment it's not. And the ADC is only in the visible, which is where you need it. Since you have 2 slits, you can split them, and it's foreseen for the 2020s. On our side, we are leading here from Granada an instrument called Octocam that is currently being proposed for its installation in the Gemini telescope, in the Gemini South. So that's the Gemini telescope, and this follows kind of the same idea of science of instrument that I explained before, but with some novel features. So here we have a multi-channel camera. We have 8 different channels observing simultaneously. So we're basically multiplying the power of the telescope by 8. We can do imaging in 8 bands simultaneously in GRI, Z, Y, J, H, K. So we have a very broad coverage, both in imaging and in spectroscopy. In spectroscopy, we cover from 3,700 to 23,500. As we have separate channels for all of them, that also improves the problems that we had before for K-band stray light. That would be much more constrained. What we're doing here is also gathering the experience that there has been with, for example, the multi-band imaging of Grand at the 2.3 in La Silla, the broadband spectroscopy of Octubre that I just presented, and the high time resolution, because we also want to go for high time resolution, inheriting a bit of the experience of UltraCam. And putting all this together is what we call Octocam, which covers an area of the diagram of temporal resolution, spectral coverage, and spectral resolution that is not covered by any other instrument in the world right now. So this, as I say, is an instrument that's being proposed currently for the 8.1 meter Gemini South, actually, in this case. This we propose in a response for the 2014 call for feasibility studies. We got this project funded for the feasibility study, among with 3 others, and we presented the feasibility study basically 1 year ago. And this year there has been the new call for instrument design. The one selected now will be the one that will be built. That has been handed in this summer, and basically in November we should know if we're granted the fundings for building the instrument or not, and we'll start the instrument in 2017, hoping to be on the telescope in 2022. The Octocam team is led from Granada. The team here has been led by me and Cristina, and we have a very strong partnership with the Southwest Research Institute in Texas. You probably know these guys. I don't know if you know the guys by the name, but they've been the ones, for example, building the New Horizons mission and many other missions for NASA. They are not so much into ground-based instrumentation, but they are wanting to get into it through this instrument. A project scientist is Alexander van der Horst from George Washington University, and we are involving very strongly Fractal into the project. Then we have some contacts in the Anglo-Australian Observatory that will be helping us with the design and construction of an integral field unit, and we have the expert in spectropolarimetry from Leiden Observatory. We also have some support from our colleagues in Italy for the gratings. And we have a very, very strong science team that Alexander managed to put together. It's almost 50 people covering basically all branches of astronomy, nighttime astronomy at least. And we have many, many science cases that would take advantage of an instrument like this. So the instrument, and I'm going to try to be a bit fast now, has a scheme that's a little bit different. So we're going for classical collimator, Grism filter, camera design. Only that we're multiplying this by 8. Part of the optics are common. So we receive the light from the telescope. We have an atmospheric dispersion corrector, and we have a single slit. In this case, we have a single slit. So what we're observing is observed by all arms simultaneously in all the spectrographs. This gives us the advantage that we can install things like an IFU or like a polarimeter, and we don't have to care so much about the influence of the differential flexures between the arms. We have a cryostat, so the slit is in the cryostat, and the cryostat contains the 4 infrared spectrographs. There's many optics that are common to reduce the size, the weight, and make it a bit more simple. And then there's a window that goes to the optical arms that are room temperature, but that have a very similar design. Here you can see a mechanical overview of the instrument. That's the focal station that distributes the light to the different instruments at Gemini. And we have a cage that holds the instrument together, the cryostat, and the optical bench. It's like an optical bench that has on one side the infrared arm, on the bottom, or the other side, the optical arms. They are the electronic cabinets. If you look inside, you see that there's a lot of optics there, but in essence, the instrument is rather simple, although there are many pieces around. As I said, it does simultaneous imaging in GRI, Z, Y, JHK, and it's using E2V frame transfer detectors in the optical, so we can read while exposing and do it pretty fast. And we are using Hawaii 2RG detectors in the near infrared. These are all very fast detectors for readout, so the dead time between exposures in optical is basically 0 because we just transfer and then do the other exposure, and in the infrared is also very fast due to the use of these detectors. The field of view is a 3. That's a bit of the expected magnitudes. The field of view is small. It's a 3 by 3 arc-minute field of view, which sounds small, but maybe it's not so small as you see now. Actually, we can use it as a 4.2 diameter field of view. And that compared to GMOS or to Flamingos, both at the same telescope, it might seem a bit small, but you have to realize that we're multiplying this by 8. We're observing 8 channels simultaneously. So the actual field covered, if you are interested in all the filters, is much larger than most of instruments that you find on an 8-meter telescope. In spectroscopy, we go down to 3,700. We don't go lower because of the coding of the telescope. That's why we don't have U-band either in the imaging. And this is because the Gemini has an extremely efficient coating. It's silver, not aluminum. And but this has the advantage in the infrared and most of the optical that it's very, very efficient. But below 4,000, it becomes less efficient than aluminum. And below 3,700 is you can see that the efficiency together with the atmosphere goes below 25%. So we decided not to go any further there. We have a long slit of 3 arc minutes. You can compare that to the 11 arc seconds that Exudo has. So we can do many other things. And that's the resolution. We have a bit above resolution 4000 in the standard mode. And we have atmospheric dispersion corrector that we're hoping to be able to use it or not use it depending on the needs of the astronomer. We have also used that fact that we have a 3 arc minute slit to design 2 integral field units, one for natural seeing and one for adaptive optics, so as Gemini delivers an adaptive optics beam, also independent of the instrument. So we have an IFU that would be 9.7 times 6.8 arc seconds with 0.4 resolution arc second resolution element, which is quite good. And you have to take into account that this is covering the full 3,700 to 23,500 angstroms. That's non-existent up to now. In the near infrared, the resolution elements are 0.08 arc seconds, and the coverage is being optimized for 9,500 to 23,500, as the beam below that wavelength is not really well corrected. As for spectropolarimetry, we have proposed also a design based on some study that Franz Schnick did in 2012 for Octubre. That was never implemented because the instrument was already the telescope and that was a bit too complicated. But we've studied this and it would work rather well for OctoCam. It's not extremely cheap, but it would open a window of science that's not available elsewhere. It's a very interesting design because it doesn't try to make an achromatic spectropolarimeter. So it just assumes that you have a chromaticity, and it uses the modulation of the known modulation of the polarization to reconstruct the spectropolarimetry. It can even go in a mode of very fast modeling of the polarization to basically single shot spectropolarimetry, only that you lose in resolution, spectral resolution there. As for time resolution, as I said, we're using optical frame transfer detectors that can read out very fast, the near infrared also, and we wanted this capacity, but we were not willing to compromise other modes for this. So we can go down to 10 Hertz full frame. Of course, you're paying a price here in radar noise, but that's okay if you're willing to go for those modes. And we can even go to 100 Hertz in window mode. Here we're taking a bit of the experience of Ultracam, and now what they're developing Hypercam. Vic Dillon is now developing Hypercam, and we're inheriting part of his experience in the development and usage of these detectors, which he's using for his Hypercam project. And here I just place here the specifications of the instrument that we have proposed. And just say that in the case of Calar Alto, which is what we're talking about here, I guess that a similar approach could be done, maybe not as complex as OctoCam, would postulate some a bit simpler design, maybe a bigger field of view, not going all the way to K-band, because K-band is always more complicated. You need a bigger cryogenic chamber, etc. Depending on what we want to do, we could reduce the resolution to get a bit smaller detectors. You could have less channels, if you may, and you can even think about doing IFU studies and polarimeter if at all interested. I'm not thinking of going forward right now with things like this, as we're already very busy with OctoCam. But I mean, we don't know what's going to happen with OctoCam, and this is a possibility that could be attractive, and I would be willing to talk about it and think of possibilities. And that was my talk. Thank you very much.
We realized yesterday that the Hawaii 2 detectors will not be available anymore. So,
but that's the Hawaii 2, but not the Hawaii 2 RG.
Ah, there you go.
Yes, because that's the Hawaii 2. Those are the old ones. So these ones also, and especially being used with the sidecar electronics, they are very, very nice, very efficient. They are different architecture. So it's a different generation.
Okay.
So we are actually thinking also on one of the designs of going for the 4K by 4K detector and putting several channels on the same detector, and that's why I'm more aware of the prices of these things. It is cheaper to go for the 4K ones, but it adds complexity if you have to put several channels in one detector.
What is limiting the size of the IFU units which you have here or in the Calar Alto or that design?
The limiting size is basically the length of the slit that you have and the width of the slitlets that you want to use. So it is a mirror design. It's not a fiber design. So we're using an advanced image slicer, like kind of what Muse is using and such. But yeah, it's basically the slit length. Could probably go a bit bigger than that, but not very much.
One last question. Did you ever consider turning the instrument for the VLT?
I have not been aware of any calls at VLT, but yeah, I mean, my first wish would be to install this at GDC, which is our telescope. And I think there would be a lot of people willing to do science with it. Actually, as you know, we did propose a similar design. It was not exactly as advanced as this one in the 2010 call of GDC for new instruments. At the time, it was not the kind of instrument that GDC was looking for. But if there would be a further call for GDC, I would be very, very happy to propose it there. Because I think right now the instrument is in a very advanced state, and we've proved with the study that we did last year that this is feasible and that it's very, very attractive. So
yes, but well, because VLT are also our telescopes.
Yes, absolutely.
I was wondering if it would be feasible to...
Yes, the thing is, there you're touching a little bit the niche that also Octubre has. So maybe although I think it could be attractive for VLT, and this is why I'm mentioning also GDC, I think it would be much more attractive for GDC because there's not such an instrument. At VLT it would be a bit harder to sell because they have some of these capacities already available. But I mean, you never know.
Thanks again, Antonio.
Well, I think that the first time that we saw the program, as we said in the opening, we are really happy just to see how many new ideas we are coming for Alto. Now, after these 2 days, now this is a reality. I mean, there are many amazing ideas. Indeed, I would say that maybe our main problem is just to choose which way we should follow, because there are many of them, and now we have to take a decision, of course, because not all of them can be implemented because a matter of time. But I think that this is a clear clue that Alto has a future, not in terms of the organization or how the structure will be for the observatory, but in terms of the science and new developments for the future. And for that, I really appreciate all the contributions, and thank you very much to all the attenders and the speakers for their contribution that are really, really helpful for the future of the observatory. Thank you very much.
And I have two things to say. First of all, we all thank the LOC members, Ana, Carolina, Gil, Salva, because this was possible because of them. And, well, as Jesus said, there are so many ideas of instrumentation, legacy projects, so I think now it's time to change ideas, to put things in common, suggestions, comments, and to try to get the best option of either instruments or legacy projects to be able to get the highest quality science with the Calar Alto facilities. So it's time for science, time for technology, time for instrumentation. Thank you very much to all of you.